Hello everyone, and thank you all for tuning in today. My name is Nicolas Bungert from Kiel University, and as my contribution to this year's DDL Christmas lectures, I want to present some data about the influence of surface energies on the suitability of additional fines. And first of all, I want to pick you up and show you where we are right now in this big field of inhalation sciences. I'm working in the formulation development of dry powder inhalers, where we basically try to aerosolize the drug particles to make it accessible via inhalation and deliver it to the lung, either as a local treatment or as an entry gate for systemic therapies. Even if it lacks of novelty, the most common and the most important formulation strategy is still the interactive blend. While mixing of fine drug particles with a coarse carrier, which is usually lactose, the drug attaches to the carrier and it detaches later on in the inhalation airstream. And one way to optimize those formulations is by adding lactose fines. These fines attach to the carrier as well and lead to an increase in fine particle fraction. Taking a look at the SEM images, we can see on the left-hand side the interactive blend without fines and on the right-hand side the interactive blend with fines. You can see that the fines are slightly larger than the drug particles and are attached to the carrier as well. The underlying principle of the fine particle fraction increase is not completely clarified yet, but 4 theories were proposed trying to explain the operating principles. In this presentation, I want to focus on 2 of them, because 2 of them are directly linked to adhesion strength. On the one hand, the saturation of active sites, fines occupying higher energy binding sites on the carrier, forcing the drug to bind on lower ones. On the other hand, the agglomeration theory, which claims during mixing, agglomerates of fines and drug are formed, and these fines, or these agglomerates, detach more easily in comparison to the pure drug. Let's dive a little bit deeper into the work of adhesion. The work of adhesion is the energy which is necessary to separate 2 interacting particles, and it is calculated by the Van As equation. You don't need to remember any of this equation, but the fact that it is dependent on the surface energy of solids. On the one hand, the dispersive or non-polar part, and on the other hand, the polar part, or you can call it acid-base part as well. So, which surface energy works best for fines? To answer this question, I set up this experimental procedure, starting with a typical mid-sized inhalation-grade lactose, Inhalac 230 from Meglin. I put the sample on a sieve shaker with a mesh size of 32 micrometer, and the result was a carrier with removed intrinsic fines, as well as the fines that were initially removed. In addition to this fine quality, I also used commercially available milled lactose fines named Inhalac 400, as well as an expired version of it, because I observed decreasing surface energies for the expired batch of Inhalac 400. One reason could be a rearrangement of crystal defects that were initially introduced during the milling process. And as API, I used ipratropium bromide. Let me show you the particle size distributions of my starting materials. The gray colored dots represent my coarse lactose carrier, without any intrinsic fines, as you can see. And the colored dots represent my different fine qualities. They all show essentially the same particle sizes. Let's go on with the surface energy. I assessed all of my raw materials in the surface energy analyzer, which provides me with surface energies independent of surface coverages. In this table I displayed the minima and maxima of the dispersive as well as the acid-base part. And when you sum these parts up, you will get the total surface energy of solids. And since the total surface energy of solids takes most interactions into account, let's just focus on those values. They show a trend of increasing surface energies for my fines. The lowest ones for the intrinsic fines of Inhalac 230, then the expired batch, and the highest surface energies for my fresh batch of Inhalac 400 milled fines. Let me show you the surface energy distributions. The yellow colored dots represent the fresh batch of Inhalac 400. You can see that it always exhibits the highest surface energies despite of the surface coverage. Please also have a look at the error bars of the orange dots representing the expired batch. It seems like expiring is a very inconsistent process. And the previously meant order of surface energy maxima is only valid until a surface coverage of approximately 5%. So I prepared 4 different interactive blends. As blank or control blend, I just mixed my carrier without intrinsic fines with my drug particles. And I took the same carrier and added specific amounts of my different fine qualities. And then the drug in a second mixing step. I prepared all of these interactive blends using the PicoMix high-shear mixer, and then I conditioned them for 1 week at 20 degrees and 45% relative humidity in advance to the aerodynamic assessment. Speaking of which, I assessed all of my interactive blends in the next generation pharmaceutical impactor with the Novalizer device. And I calculated the results for different cutoffs, just to see if any trends continue at lower cutoffs, and they do. But please just focus on the most common cutoff of 5 micrometer. With adding the intrinsic fines that were initially removed to my carrier without fines, I was able to increase the fine particle fraction by nearly 22%. By adding the expired batch of Inalac 400 fines, the fine particle fraction increased by 65%, and last but obviously not least, the addition of a fresh batch of Inalac 400 led to a fine particle fraction increase of nearly 82%. All of these increases are statistically significant. And now, to bridge this aerodynamic data with the surface energy data, I calculated the work of adhesion. First of all, the work of adhesion, which represents the interaction of the saturation of active sites. So the work of adhesion between carrier and fines. I plotted the total work of adhesion over surface coverage. And you can see the work of adhesion decreases in basically the same order than the fine particle fractions. Another interesting point is that the differences between the milled batches are noticeably smaller than between milled and intrinsic. We remember the milled batches led to fine particle fractions of 42 and 46%, while the intrinsic fine just led to a fine particle fraction of 31%. Secondly, I calculated the work of adhesion between lactose and drug particles, which represents the formation of agglomerates, at least for the fines and drug bindings. The lowest thermodynamic work of adhesion is exhibited by the drug-carrier interaction, which is very interesting because one could assume that if carrier and fines both offer binding sites from a drug, the drug will primarily bind on the fines. And again, the work of adhesion for the fines decreases in the same order as for the fine particle fractions. So let me conclude. Higher surface energy of solids lead to higher adhesion properties, which supports the active site saturation as well as the formation of agglomerates. And one could assume that higher surface energies in general lead to higher fine particle fractions of the respective blend. With this statement, I want to finish my presentation. I want to thank you all for your attention and for listening, of course. I also want to thank my supervisor, Professor Charlize, and my whole team, and of course Megle, for their support. And since scientific discussion is what makes science effective, please do not hesitate to get in touch with me and discuss my data with me. Thank you all again and enjoy the rest of the DDL Christmas lectures.